Hello and welcome back to Calculus 3. This is going to be our second part of line integrals. And in this lecture we are going to explore circulation and flux and whatever else is missing that we haven't covered last time. So it's a very long section, obviously. We talked about the line integrals yesterday, and I made this comparison between Calculus 1 and Calculus 3, where in Calculus 1 you are calculating area under the curve, but that if you want to think about the shaded part over there as a curtain, that curtain is flat, where the curtain on the bottom is actually wavy and curved. So the bottom one calculates the area using what we call the line integral. And then we had few forms of the line integral, and then we talked about the vector field, so calculating line integrals in the vector field. So now when we have these equations, we are going to talk about circulation and the flux of a vector field. These are very important concepts in many of the engineering areas. If you are thinking of electrical engineering, you will see a lot of this stuff in electromagnetism and so on. So, so I guess pay attention, right? We'll start with circulation. So let's write definition and then we'll talk about it. So definition for circulation. So let vector field, right? So let F with the arrow be a continuous vector field on a region D of R3, and let C be a closed, smooth, oriented curve in D. The circulation of F on C is the line integral of F dot T ds, where T is the unit vector tangent to the C, where T is the unit vector tangent to C consistent with the orientation. All right, so now to calculate circulation, I hope you hear the word circle in it, and I hope you are trying to connect this to some type of rotation, because now we are going to consider circulation of the radial field, and we are going to consider the circulation of a rotational field. What do you think? Which one is going to have a circulation? Rotational field, right? Because rotational field is going to move the field, right? It's rotating, so there's like air is circulating. Okay, you can think of the basic wording to help you with the concepts that are happening here. Yes.
So what is the difference between that formula and formula?
No difference. No difference. This is adding a word to it, and it's computing this particular concept that it's actually just moving stuff around. So we are going to take a look at the radial field given by vector f, which is the vector field, just xy. I hope we are on a unit disk. Please be on a unit disk. Thank you for being on a unit disk. So now on unit disk. And now when you see a unit disk, the circumference of that disk is a unit circle, and the parametrization of the unit circle is going to be very simple. So we have our closed, oriented, smooth curve, right, that we can parametricize. So I'm going to immediately go with the green over here and say R is equal to, and I have it should be R cosine theta or R cosine t, but I'm going to use, since it's a unit disk, so R is 1, so I just have cosine t sine t. Right, that's that. And then I have the R prime, which is negative sine t cosine t. And to calculate our circulation, this is the good old integral from yesterday, which is exactly the same. So we know that we can write this same integral as integral a to b with the vector field dotted with r prime dt. So that's from yesterday. So now what do I have? I have 0 to 2 pi because t, to trace the entire circle, we have from 0 to 2 pi. And then we have the vector field f. Now vector field f, if you remember the drill over here, your f is x and the y, so you have your cosine goes for x value over there, so I have the vector here that says cosine t comma sine t, so that's my f, and then I dot that with the r prime, which is negative sine t cosine t dt. Now we have the dot product. Let me put that here. That's a dot product. You know what's going to happen as you do the dot product, right? So you're just going to say now this is integral 0 to 2 pi. And you have a cosine times negative sine. You have negative sine t cosine t plus sine t cosine t, everything dt. And I hope you see that's 0, because you have the integral of 0 dt, which is 0. So radial field has 0 circulation, which makes sense because the picture for the radial field would be something like this. You have your unit disk, and it radiates out. There is nothing circling around. Everything is just getting from the source, getting out, away from, right, the source. So circulation is 0. Now, if we take a look for the circulation using rotational field, and I have rotational field F that is going to be given as negative yx, again on unit disk, I have the same parameterization. So unit disk is going to give me r is equal to cosine t sine t. and r prime, the derivative, is negative sine t cosine t. Great. So now, when I work out the integral, so we have f dot t ds, but we know that's a to b of f dot r derivative dt. So we have again 0 to 2 pi because we want the full disk, and then we have the f, which is given now as negative sine t comma cosine t dotted with negative sine t cosine t dt. If you have trouble of following this, well, I'll direct you to yesterday's video to 4.2 part 1, because there I am telling you that this one over here is your x, and x is over here, so that one plugs in there. The other one is y, so that's why it's a negative sign. Now these two are the same, so when I dot these two, I get sine squared t plus cosine squared t everything dt, and that's just integral 0 to 2 pi of 1 dt, which is 2 pi. So now we see that for rotational field, we have that circulation is 2 pi. So that's going to be, we can draw again the image for this. Now we are going to have over here the circulation. So this is what the rotational field looks like. We have over here the radius is equal to 1 because it's a unit disk, and you can see the circulation because the whole thing is trying to spin. So that's the circulation part. We haven't learned anything new in terms of the formulas because this is the same integral you calculated yesterday. We're just adding the concept to the whole thing. And now it's time to look at the flux. So flux, first, before I do any of the equations and definitions and things, I just want to tell you that the flux is how much stuff is going to be passing through an area perpendicular to that area. And the best way to understand flux is just to look at the fan, right? The fan, when you turn it on, this is let's call this a unit disk. Over here, you are going to have all of the vector fields, so all of these infinitely many vectors going straight out of the fan. So when I turn on the fan, you are actually seeing, oh come on. So that's, you can see there's nothing over here, right? There's stuff over there. So how much stuff is being pushed forward in terms of the vector field, where circulation is all of the stuff that is happening at the edge, and in terms of is there a rotational field, or here like those Dyson things that have no propellers, they are using these kind of concepts. I mean, if you want to design these kind of things, you have to understand these concepts. You can't just show up and say, I graduated. It's like me, I ran twice in my life to catch the train or a bus, and now I'm a star athlete. It's like, yeah, that's you graduating, asking for a job.
Are you saying C's that get degrees is not like a correct term?
It is. C's do get degrees, and they can't keep their jobs. So, all right. So let's talk about flux now. Hold on. Whoa, spazzed out. There we go. Flux. It's a bit lengthy definition. I hope you understood what I gave you with the fan. All right, so let vector f, which is given as fg, right? We have those two functions in there, be a continuous vector field on region R in R2. Let C be parametricized, right? So we have R of t is equal to x of t, y of t for a less equal than t less equal than b. So that's the interval for t. Be a smooth oriented curve in R. That does not intersect itself. The flux on the vector field F across C so the flux of the vector field F across C is, and here's the formula, so we have the integration C F dot n. Now that should make sense. ds, we are using the normal vector because we want the stuff that is perpendicular and leaving the fan. Now we have to convert this and put it in a form that we can compute. So it's going to be f of t y prime of t minus g of t x prime of t dt. So we have some of the clarifications here. The vector n, right, is the unit normal vector, which is going to be vector t, which is a unit vector crossed with the k, right? So we have that, and then t is the unit tangent vector. Well, I'm going to use the same problems now. I want to calculate the flux for a radial field, and I want to calculate flux for rotational field, right? So let's go with the radial field. So radial field will have that f is equal to xy, and again on unit disk. So I have my r as cosine t sine t, and my r prime as negative sine t cosine t. And I am going to calculate now the flux by computing the integral of f dot n ds is equal to the integral. I don't want to write the formula again, it's up there. So we know it's 0 to 2 pi because our parameterization for unit disk worked as that. And then we have the, so we now have to chase all of these values. So f of t is x, and x is cosine t, okay, fine, times y prime, well that's cosine t, minus, gt is sine t, times the derivative of x, which is negative sine t, and all of that dt. I hope you see immediately it's 0 to 2 pi
And it's also 1.
of, yes, cosine squared t plus sine squared t dt, which is you are integrating 1 dt from 0 to 2 pi, so it has to be 2 pi. So now you see that circulation for the radial field was 0, but the flux for radial field is 2 pi. We are expecting to see flux for the rotational field to be 0 because there is nothing perpendicular that it's leaving the... So let's take a look at the rotational field. So for rotational field, we know, I don't know if you already memorized or you haven't memorized, but rotational field is so negative y comma x, and then we have our good old unit disk, which is given as r cosine t sine t, and then these are vectors, right? And then r prime is negative sine t cosine t. So once we have this, we are going to compile, well, let's first write this f dot n ds, which is the flux is equal to integral 0 to 2 pi, and now I have the negative y, that's negative sine t, times, wait, what is this? Yes. Yes, this is x. The true spirit of the social justice, right? Yeah. So we have f times y prime. So f is y, negative y, so that's negative sine t, and then I need y prime, which is cosine t. Yeah. Plus x is cosine t.
Why is it plus?
I don't know why it's plus, it's a minus. And then minus sine t over here. There we go. And then dt. Much better. It's 0. Of course it's going to be 0. You have a rotational field and you have flux. See, if you want to think about it.
So that's the equation.
What does flux even mean?
I talked about it.
Okay, so it's the pushing thing. So when you rotate, you don't push things?
Exactly.
It's how particles are moved, right?
The particles are not moving perpendicular away from the...
Okay.
Right.
They're perpendicular.
So,
to the force.
well, look.
Rotational, none of the particles.
Well, let me just finish this problem. So this is again integral of 0, dt is equal to 0, and problem is
The
solved.
force is going out, right?
So guys,
it's perpendicular to the force when it's going this way. This part is going this way.
there we go. One more time.
I think I get it.
Flux. You can feel it, right? Circulation. There's nothing.
Well, if you put on the back end, there is.
What? Yeah, whatever. If you have a different device, obviously, yeah.
It's
But
perpendicular to an area. What area? To the front of the front.
because look,
Is the area like
so for some people will be easier, and obviously for you it's going to be beneficial. If you guys have, or if you are in physics and there's gravitational field, guys, for the gravitational field right now, there are gravity is a force, right? It's going to go through this sheet of paper, right? And then look, it's all of the force that goes through this, right, which is why it applies to this area. And as you can see, the paper, now obviously there is air resistance. There's air resistance to it. So the whole thing is all in these fields. I mean, you have gravitational field, electric field, magnetic field, right? All of the fields are there. The idea is that all of that force, all of the vectors that are representing the force of which is actually in this case it's force times the mass, gravity, sorry, is going to give the mass to this object. So it has to fall because it sits in gravitational field. When you are far away from big celestial objects that create gravitational field, so there is no gravitational field, or say you work in a microgravity, things float about, right? Flux is zero. All right, flux is zero on the surface. So these are the things that on the surface of the rock.
On the rock between two fields.
No, surface of the rock. So if you take the cross section of the rock on that surface, right, the flux is zero. Okay. This is no gravitational. So these are the things that you actually have to stop, sit, and think about and try to read in a book, but then pick up the physics textbook, try to understand either looking at the gravitational field or electric field, or find other YouTube videos on the thing to try to see a different perspective, right? Just a different accent will help a lot. So yeah, that works too.
I'll look up a nice French accent.
Yes, there you go. Look up French accent.
I'll ask French along. He has a French accent. Isn't his accent?
Professor, what does your say? Like, squares -1.
God. What's the square root of a negative number? And what is that represented as? I. And then what's 2 to the 3rd?
Oh, it's not really sure.
Yeah. I, 8, and then some.
Yeah, 8 summation pi. I don't get that.
I hate it.
Okay,
It's
good to
called
know.
I.
All right, so I guess that's it. Unless you want to try another circulation or another flux,
What would be different?
just a different field.
Okay.
Because our fields were radial field and rotational field, the most basic two fields that you can get. Maybe we can let's calculate circulation and flux for a bit more complex field, something that it's a little bit more spicy. So let's go with F. So that's terrible. There we go. So F is given as y minus x comma x on circle of radius 2. Get both circulation and flux. Area grows in the square of the radius.
Okay, it's like, wait, am I looking for the one?
All over me. So please stop.
Just like how nice and Jesus.
Then you will just have a function. Just so you have like this. Tons of fun, right? No? Aw. Well, at least you're smiling. There's that. All right. I'm going to parametricize as 2 cosine t to sine t, and I need r prime, which is negative 2 sine t, 2 cosine t. There we go. All right, so let's start with circulation. We have f dot r prime dt. F is, well, integral 0 to 2 pi. F is a vector, so I have y minus x, so that's 2 sine t minus 2 cosine t, comma 2 cosine t. So this is my f times negative 2 sine t to cosine t dt. 0 to pi. Now we have to do the dot product. So negative 4 sine squared t plus 4 sine t cosine t. So that's that. Plus 4 cosine squared t, close parenthesis, dt. Is this good? No?
Wait, no, yeah, that's good. Wait, no, it's supposed to be sine.
Oh, no, it's...
Yeah, it's supposed to be negative 4 sine squared plus 4 sine t, and then plus 4 sine squared again.
Wait, I have this.
Oh, wait, yeah, you got it right.
I got sine squared.
Well, hold on. So we have y, which is 2 sine t, minus 2 cosine t, comma, cosine t, dotted with negative 2 sine t, 2 cosine t. I know. Now, when I multiply negative 4 sine squared, positive 4 sine cosine, and then 2 cosine times 2 cosine is plus 4 cosine squared. We're good, right? Yeah. All right, so now, how are your trig entities, huh? Well, first let's kick out 4, because all of these have 4. And then I have this sine t cosine t. Oh, I shouldn't be kicking 4. No, because I need a 2 for here. I need to keep 2, so I have to kick 2 out, actually. I need to keep 2, so I'll leave this term, and then I will go plus 2 times, and in parentheses I'll put cosine squared t minus sine squared t. Does anyone know what this is?
Which one? The 2 sine?
Yeah, well, both of these.
Well, the one it was simply going to be sine 2 beta.
Yes. So this is sine 2t, nice. Plus, what's the other one?
Oh, that's going to be
cosine 2t, nice. Yeah, it's basic pre-calculus, exactly. So now we are going to integrate these puppies. I have 2 times integral, so now it's integral of sine is negative cosine 2t divided by 2 plus 2 times sine 2t divided by 2 computed from 0 to 2 pi. So now this 2 will kill this 2. This 2 will kill this 2, but then there will be 2 for the other one when you distribute. So I have negative cosine 2t plus 2 sine 2t computed from 0 to 2 pi. And now, when we plug values in, we have negative cosine of 4 pi plus 2 sine of 4 pi. Minus and minus give me plus cosine of 0. And then minus 2. This is not important because it's sine of 0, so who cares? Now, cosine at any even integer of pi is 1. So I have negative 1 plus 0 plus 1 minus 0, and we get big fat 0. Flux. Yeah.
Okay.
So what is there for flux? We have the integral of f of t y prime of t minus g of t x prime of t everything dt from 0 to 2 pi. Well, I should put a to b and then figure the rest out. So now my f was y minus x, so that was cos 2, was that was 2 sine negative 2 sine? No. 2 sine t minus 2 cosine t times y prime. Y prime is supposed to be cosine t minus g of t was the second one, so that's sine t times x prime, and that's negative. That's negative sine t dt from 0 to 2 pi on the integral. I forgot that.
Put it all to for the x, for like the t.
No, I'm missing a 2 somewhere. No, I'm missing 2's everywhere, right?
Okay.
Yeah, I'm missing 2's everywhere. Good. Alright, so now what do I have? I have 4 sine t cosine t minus 4 cosine squared t plus 2 sine squared t dt, and we'll do the same wait, no, this is a 4, not 2. We'll do the same trick. Well, I need to kick negative 2 out now, because I need cosine minus sine, not sine minus cosine. So I need to kick 2 out, 0 to 2 pi, and when I kick those out, I'm going to write this first now. So I have 2 times the cosine squared t minus sine squared t, so that's that, and then we have a minus 2 sine t cosine t, and then everything dt. So now with the negative 2, integral 0 to 2 pi, we simplify this cosine minus sine, that's 2 cosine 2t minus 2 sine 2t. No, it's just minus sine 2t. There we go. And then dt. Because the 2 is the part of the formula. Sine 2t is 2 sine cosine. So that 2 is absorbed by the formula. I'm happy that I caught that. Now, if you want to, you can distribute this minus sign inside and swap the term, the order, but who cares? Negative 2, the integral of cosine is positive sine, so I have 2 sine 2t divided by 2, so these will die. And then minus integral of this is negative cosine, so I have negative cosine 2t over 2. Computed from 0 to 2 pi. So now I have negative 2 sine 2t, triple negative, so that's a minus, cosine 2t, computed from 0 to 2 pi. So now when I plug everything into sine term just dies. So I have negative cosine of 4 pi, minus and minus give me plus cosine of 0. Yeah, but I also distributed 2. Oh, which I didn't write. Yeah.
No, plus is out though.
So, is it good? Is everyone happy? All right. So we can go for a break, right? If everyone is happy. All right, good. See you after the break.